Hello, this is Gabe Shaughnessy. I was just sharing some progress I've made on the AstroImaging planner. I haven't made a video of this yet, and I thought it would be a good time to do that, to show how it works and how it all fits together with Voyager. So this is the first tab that you're shown with. It pulls in all of the targets that are in the Voyager RoboClip database, and they're organized by group. And here I have, for all my groups, I use profile names. The first one is the telescope. In the profile name, the first entry here is the telescope, and then the sensor. And I have a few others for different telescopes and sensors. And that's how I organize my my RoboClip database. And you can change these, and the targets that are in the RoboClip database will get updated in this map across the sky. So you have altitude over the duration through the night, and you hover over here and you can see the altitude at any given time, along with any notes that you put into the RoboClip database. I also have a way that you can specify a custom horizon so that if the object falls below that horizon, maybe a tree line or a house or something, that it no longer shows up in this sort of bold line here. So you know then that that target is outside of kind of your observable window. I have a few other things here, altitude and air mass. I think personally, I think altitude is probably more more useful for me in my planning, but I put in air mass as well. I also have in the code, I also have a way to calculate contrast as well, and that takes into account the moon, the altitude of the moon, and how far away the moon is from the target that you're shooting. There are a couple filters in here for, well, a couple ways that you can filter out the different filters you're using. For example, if you know the moon is up and you only want to image through with broadband or with narrowband filters, then it removes all the targets that are only broadband. And the way I track that is in the notes, I put, LRGB or HA or O3 and so on. That way in the notes in the RoboClip database, it gets tracked in the filters here. And then one thing in the imaging planner that I have set up is a target status. So you can have a lot of different targets that you're trying to shoot throughout the year, and it's helpful to keep track of what the status of each is. And I have 4 different types of status. One is pending, which is a type of target I have not shot yet. One is active, where I'm making progress in the current nights as I'm imaging. And then I have a few others acquired, where I think I have enough data to go forward with processing it, and then close, which is I've acquired it, I've processed it, I'm happy with the result, and I can be done with it. So right now I just have the pending and active targets that are selected, and those are shown up here as well as down here. And if I, for example, only want to look at the active, then the targets change accordingly. If I want to look at any of the closed targets that I've done throughout my time with this setup, then you can see those as well. And then you have a way that you can select an object and then change its status. So this status applies to a particular object that you've been shooting, and as you go on, you can change that status here. And then some, your location on the Earth, altitude, latitude, longitude, universal time offset, and so on. For people in the US, I also have this button here where it'll pull the weather forecast from the National Weather Service and plot it here. Probably the most important one for astronomy is cloud amount. So you can see right now around here we have pretty crummy weather in the winter, but this can help you kind of track to see if you're having a clear night coming up or whatever. Up here there's a link to the project repository, which is right here. It kind of steps you through how to set it up and so on. I also have, depending on your latitude, longitude, these links here will update. This is the Clear Outside report, which is a helpful website for figuring out if the nights are favorable for you. Currently, it's not loading, I guess, but the National Weather Service is another one that's linked there as well. And then the satellite forecast. Right now, it's centered over. I live in Wisconsin, so it's centered over here. You can change that as well in the code if you like. And then a smoke forecast, which in the summer months in North America, we get a lot of smoke, and this is just from the wildfires either in the West or in Canada, and this is a way to kind of see if you're going to be ruined by smoke in the upper atmosphere. So this is one sort of page for this. Actually, before I move on, I want to step through this a little bit more. With any of these plots, you can zoom in. Just make a box and then double click to come out. All these plots are built off of Dash, which is based off of Python. It's a plotting routine that's used a lot in dashboard apps and data science and things like that. So one thing you can do is, one thing that I do when I look at this and I want to plan a night, I always select the moon. And right now, I guess the moon it's a new moon, so let's travel to a time when the moon is is out. So we can select the moon. Here's the moon, and then we want to plan around it. So maybe, but we can start to see when some of these objects have lower latitude or lower altitude than the other objects. Usually around there, more or less, is when I start to transition from one object to another, depending on how much time is needed for that object and how much time I have left in the night. So this is one way to help me plan the timings of when I transition from one object to another. So this kind of selection can help, especially in the case where you have a lot of targets. For example, with this setup, I have a lot of targets planned because it's a high resolution. You have a lot more possible targets to go after. And it's kind of a mess right here, but when you select the moon, you can start to add on the other targets and sort of plan your night as you see fit. So it's kind of nice. Likewise, down here, we can zoom in on a particular region. When we hover over these, we see how much total exposure we have for this object under this filter. So this is actually looking at the data you've stored on disk to keep track of that, and it breaks it down by the sensor that you're using. So this is a QSI 690, and then the binning, it's 1 by 1, and then the focal length. So this is the my 10-inch reflecting telescope at 1150 millimeters. So these things kind of help you keep track of how much data you have so far, and then depending on how much data you have, you can come over here and change the target status. Okay, the next tab here is reviewing stored targets. So these are all the targets that have been stored. And initially it looks like this table is pretty crowded and maybe too much information or something, but it can be helpful when you want to drill down into something. So say that this top row is kind of an area where you can do additional filters to kind of drill down into the table a bit more. So say I want to look at what targets I have more than 4 hours of luminance data, and you just put in this this filter here, and that filters out all the objects, and that way you can look at what objects you have that that much luminance data with. Or maybe I want to look at only the targets that I've done with my 10-inch Newtonian. You could do that as well. So this can be helpful with kind of drilling down to see where targets are in terms of the amount of data you have, their looking through the notes, maybe you put in your note something like Gecko Nebula. Gecko Nebula. So if you know that it was the Gecko Nebula, but you forgot the designation, you can go through and filter your data that way as well. So yeah, this is just a nice little table to have where all your data stored is here, and you can see how much exposure you have. It's really no different than here, but here it's broken down by your profile, and this is all the data that you have stored. Another thing that I recently added is the ability to review stored subframes. And this is what this is doing is it's pulling in all of the subframes you have stored on disk, analyzing it. So it's actually identifying all the stars, the shape of those stars, the distribution of stars, and the distribution of the shapes. So some stars will have kind of a more radial flaring, and that can maybe indicate an issue with spacing of a field flattener or something with your chip. And some stars will have more of an arc, a circular arc around the center, and that could also indicate a spacing issue. So this is just kind of a way to pull in all that data and take a look at how that distribution looks. I have, as a default, I have full width half max of the average full width half max of stars. And then along here is the eccentricity of those stars. So the higher eccentricity means the more elongated that star is on average. Obviously, the higher full width half max, the more bloated that star is. So you can see, for example, maybe this green frame here. Once you click on one of these points, then an inspector preview, just like you get in PixInsight, shows up over here. And you can turn this off. You can actually view the full frame by turning that off. And it takes a little while to load because it is pulling in the entire frame. And then you can zoom in this preview as well. And then again, double click to zoom out. Turn that back on. But in any case, you can see that for the most part, these stars are pretty well rounded. But if you take another green sample up here with higher eccentricity and you zoom in, you see that the stars are more elongated in one direction, just a tiny bit. Also, you probably will see more elongation in the corners as well. So this is kind of a nice way to show whether you're having issues either with star bloat or star maybe drift, maybe your tracking isn't great, maybe you're having a lot of wind issues or something, and this is one way to do it. Another way to do that is what I've done is within the full frame, I take let me wait for this to load. Okay, so within the full frame, I would take within a square however many stars are here and average the metrics of those stars, and then count that in this view, which shows how the stars are aggregated across the frame. The color here is full width half max, and I have it set between 1 and 5. So we see that these are all pretty low, 2.2 in the middle, and it kind of varies between 1.5 to 2.5, something like that. But I also added this line that shows the direction of the elongation. And that can be helpful, like I was saying earlier, where you can have, depending on the spacing of your chip to sensor, you can have, radial elongation or sort of a circular elongation or azimuthal elongation, which is indicative of a different spacing issue, either too close or too far from the sensor, is the field flattener element. So, so this is kind of showing that in this case, a lot of the directions are in one direction. So this could be more drift, either through tracking or maybe it was a very windy night, in which case I was getting a lot of motion in this direction. And then this plot just shows the distance from the center, what the average ellipticity is, and then the average full width half max. And in some cases, you'll have the ellipticity increase as you go beyond sort of the imaging circle of your setup. Likewise with the full width half max, and this is just a way to kind of distill this plot into this. So we can look at a few other examples. Again, 31 is one of them. I'm actually running it right now. It hasn't loaded that one. I'm regenerating the database that goes behind this. We can go into a couple others. Yeah, okay. This one was done with a telescope and field flattener that did have some of those issues, I think. If it comes up. Oh, I'm going to turn off the inspector, that preview. So here we have more sort of radial elongation, and that's more indicative of that field flattener spacing issue. And so the idea would be to track this and see if we can change the spacing a little bit and get a better result here. So this way we can numerically track if we're actually doing better or if we're doing worse. All right, and then down here there's a summary. So of all the objects under the propeller nebula, of all the frames that I've taken, it filters, it aggregates them down into the different filters that I've taken with this object. And it shows the binning, the focal length that was taken, the pixel size in microns, the total exposure, so half an hour for the RGB, and then 2, 4, and almost 5 for the narrowband. What I call CCD temperature dispersion, which is more or less the standard deviation of all the CCD temperatures over the course of the acquisition. Say for this filter, the standard deviation was around 3 degrees Celsius, which is rather large. So if I see this being around 3, I might start to worry and think that I might be using the wrong calibration frames if I use them for all of those frames, because those temperatures will be different across this set of frames. And then the number of subs that contribute to the total exposure. And then further down, you can even drill down into the individual subs. You have all of the FITS header entries available to filter through. And this filtering is the same as the filtering that was in this table as well. So yeah, you can add other other options. So file name, if you want to find the file name that is associated with maybe some anomalous eccentricity or elongation. Let's see, I have a lot of data here that you can run through. The number of stars that have been detected. So we're getting into the thousands of stars across that entire frame. Another thing that I came up with is what I call star trail strength. And what this is kind of the this radial drift that we see, or not radial drift, but a sort of uniform drift of these lines, which indicates that all the stars are trailing in one direction. And if that happens, then this star trail strength will be large. So we can sort this strength. And anything much larger than 2 is where you start to worry. So 2.89 isn't that big of a deal. We can actually use, because all of these things are common. I can filter it down here, but I can also filter it up here. So star trail strength, and maybe I'll look for one. Okay, that one maxes out at 2.6. Just trying to find one that's relatively high, 3.5. Okay, let's try this one. In this case, you can see that the star is kind of elongated in this direction. Likewise, these are kind of elongated as well. And you see that these are all elongated in one direction. And that's more indicative of trailing. Either your tracking motion is off, or you're getting really bad guiding in one direction, or you have a lot of wind or something kind of kicking up your mount and pushing it along. So whenever this star trail strength is large, that might be a type of frame you might want to reject, because you're losing your sensitivity to getting really tightly focused stars. I also have as options some quick options here. So this is full width half max versus eccentricity. This is the first one that we looked at. Another is altitude versus azimuth. And for the use case for this would be, for example, if you do a meridian flip and you want to inspect your frames down here to see if the frames are behaving in a different way. And that might be indicative of flexure either in your imaging train or maybe even in your mount with tracking to increase, full width half max of your stars and so on. Background sky level versus the star count. This is particularly helpful in cases where you're imaging night to night, and sometimes you're having a higher background, maybe because of fog or maybe because higher light pollution or something like that. And you can see how the background sky level and star count kind of have this trade-off between the two of them. So let me get a good example here of this, just to illustrate. Let's see. Okay. So in this case, the background value, luminance is, this is a LRG-BHA for this galaxy. Luminance is going to have the highest background and the highest number of stars, but within a color band, you see this sort of general trend up and to the left. Green and blue are relatively the same, and then red has a lot lower background but a lot higher star count. It's kind of interesting. Focus position versus temperature. You could use this type of plot to measure your focus drift through the night due to thermal expansion or thermal contraction and the deformation of the lens as well. Full width half max standard deviation versus mean. I've used this to detect satellites and star trail, planes. When you have a main branch and then one point that's way off, that's usually because the star detector picked the plane trail or the satellite trail as a very, very elongated star. So that's a good way to detect planes and things like that. And then altitude versus background. So this is another one where you can measure, as the object gets higher over the night, how the background changes, and potentially even map your local light pollution levels with this. And that's something I've thought about adding to this as well, to have some sort of automatic light pollution measurement. But it's still early. Eventually what I want to do is have a way to automatically grade these based off of some sort of outlier rejection. So if we have within a sample of luminance some frames that have a lot of very high eccentricity, high elongation, we can reject those and have that reflect automatically in these types of plots, so that you don't have to always drill down into these to determine what's good and what's bad. So that way you can, maybe your rate of bad subs is 10%, but still you'll get an idea of what's of what good data you have left. So yeah, that's this AstroImaging planner. I've actually built a separate version of this that lives outside of the AstroImaging planner, because this framework has it's all built on Docker, which is a technology to containerize services. So it has it's built off of Dash, which is what the dashboard is built out of, but also a Postgres database that stores all of the data after the stars are measured and so on. So if you don't want all that, but you want something like this, I wrote another version of it that is just standalone. So it doesn't have any dependency on the database or RoboClip or anything like that. All you have to do is just add a couple FITS files, and it churns through them. Right now it's kind of limited to how much you can push through it, but you can add probably half a dozen or so files to kind of inspect them, and you can get plots like this, as well as the the frame analysis plot like this. So yeah, that's kind of the update I have for this project. It's been fun and continuing to add to it. So thanks for watching.